So we are looking at the Indian monsoon, and we will get into the context of monsoon response to global warming. But in the meantime, we looked at the basic processes, the introduction to the onset, the intra-seasonal variability, which is very dominant, and we are slowly moving into what the responses are. So we looked at the homogeneous region typically that is studied when we want to do monsoon statistics, called the core monsoon zone, and we argued that the all India rainfall and the core monsoon zone have very high correlation. So the histograms here are monthly means for each month of the monsoon season in each year, and the thick black line is some kind of a running average. Usually you take a time series like this and you make like a 5-year or 10-year running mean, which gives you a sense of the decadal or longer time scale variability, which tells us the low frequency monsoon variability is happening. So you, as we said, we have decades where monsoon remains above the long term mean, and then decades where it's below, and so on and so forth. So what is actually happening that we can tell from the observations before we can attribute it to climate change or global warming? So we are always doing first the detection, and then we want to attribute the causes to the signal we are detecting. So this is the first plot. So this is from the same paper that I mentioned, and this is showing the variance of monsoon going from the 1950 to about 2005 or 6, and you can see that the daily variance of rainfall has been increasing, which means if you had an average of 10 millimeter per day on a given calendar day, for example, let's say August 15th, then the range used to be, let's say, 5 millimeters to about 12 millimeters on average. But over these few decades, this range is now becoming something like 1 millimeter to 20 millimeters or something. So this variance in a given day, you can do it as a simple standard deviation. This is why the units are millimeters squared per day squared, whereas rainfall is usually millimeters per day, right? So you can also see that along with it, we have the Indian Ocean SST and its coefficient of variance, which is essentially the anomalies divided by the standard deviation. You don't have to necessarily know the detail, but you can also pick it up very easily from a simple statistical book. So the Indian Ocean temperature is warming. That corresponds to the increase in variance of rainfall over this core monsoon zone. What does that mean? Usually, statistically speaking, we don't take the correlations between two trends to be immediately indication of a cause and effect. So the correlations are always high between two things that are varying in time, because the trends always correlate, whether it goes this way or that way. Correlation can be negative or positive, but you have to have additional information to make mechanistic links. So the simple rule to remember, as you probably already know, is that correlation is not causality. So you have to first find the correlation and then try to explain the processes which explain the causes of the correlation. Then you can say what are the processes that are causing the forcing of one, let's say the monsoon rainfall by sea surface temperature over the Indian Ocean. Now this is getting more specific. This is showing rainfall events of greater than 100 millimeters per day. That is a significant amount of rain. This is what you would call an extreme rain, where extreme is typically, let's say, defined by when the rain is within the 95th percentile of a typical rain during that day. So as I said, if the rain on August 15th varies between 5 millimeters and 12 millimeters, you can make a statistical distribution and say if it's close to 12 millimeters, then you are in the upper percentile, close to the extreme you can expect during that day. So 100 millimeters is a very heavy rain event, and it's also looking at events that are less than 100 millimeters per day. We say greater than 5 millimeters per day because when it gets too small in the amount, then it's basically like drizzle. So we want to have rain rates that are significant at some level. So you can see that the rain rates of greater than 100 millimeters per day are increasing over this time. Doesn't mean that every event is 100 millimeters, but you can see that they also have an up and down. Nonetheless, they are increasing over this period, while the 5 to 100 millimeters per day have been decreasing. So, how do you think of this? And this is also the same for when you look at even events that are greater than 150 millimeters per day, which is much larger than 100 millimeters per day. So, 100 millimeters per day may not sound like much, but if you think of a region, let's say the size of Bombay, and if it rains 100 millimeters in a day over Bombay, you take the area, multiply the area by the amount of rain you would get with 100 millimeters, and you calculate how many buckets of water that is. That's going to be massive amount of water that is going to cause floods. So, this here means that if it is pouring like crazy on some part of Kerala, if this is India and Kerala is in this corner, so Sri Lanka is here. If it is raining like crazy over here, let's say greater than 150 millimeters per day, that means that water is essentially being taken up from the neighbors somehow. So, it cannot rain 100 millimeters per day or 150 millimeters per day everywhere, because that would require the entire ocean to be evaporating massively. That does not happen. And the water has to be transported, which also takes time, because it has to come hundreds and sometimes thousands of kilometers from the source where evaporation happens. So, that means if you increase extremes, and then you in general are taking that rain away from lower amounts of rainfall that should be happening around. Okay? That is the general idea, but the main idea is that the extreme events have increased. So, this is a signal that has been detected, and you can show that this is statistically significant and so on. But there are obviously complications. This is a paper by Subimal Ghosh of IIT Bombay, which shows that if you look at the trends in spatial variability of the Indian summer monsoon rainfall from 1951 to 2004, which is essentially the same period, then the trend in spatial variability of the mean monsoon rainfall. So, you take the average over the whole summer season, average over all of India, and see how its spatial variability is changing over time. And you can see that that spatial variability shows a downward trend. But if you look at the trend in spatial variability of the extreme rainfall corresponding to the 50-year period, return period, which I will say what it is in a minute. So, the extreme rainfalls are increasing in spatial variability. So, go back to our popcorn kettle and the corns. Okay? So, in a normal rainfall condition, you can imagine that corns are popping everywhere by similar frequency, let us say. So, it looks like there are corns popping everywhere, you do not see any difference. But when there is extreme event, suddenly in one corner there is like a fireworks going on, lots of corns popping here and not much happening here. And this spatial variability increase means the corns begin to pop everywhere much more frequently. So, it is the time rate of change. So, heavy events are increasing in time, and this is saying that heavy events are also increasing in the spatial distribution, and I will come back and show what this means. But it is the spatial variability and time variability that we are always concerned about. Another work by Deepti Singh from Stanford University kind of put more subtle points on many studies that had been done before, which is showing that the mean rainfall over India has been decreasing, but the variability has been increasing over essentially again the same period, but now this goes further into 2012 or so. These are the probability distribution functions which we will not get into. So, this is consistent even if extreme events are increasing, the mean rainfall can decrease, which means the seasonal total amount of rainfall for India, let's say, it is around 900 millimeters per year for the season over all of India. The amount can decrease and become, let's say, 880 millimeters per day over these periods, but the rain is now coming as heavier events. Okay? So, again remembering length of day, number of rainy days and intensity of rain, this says that overall rainfall amount is decreasing, but the intensity is increasing and the frequency is happening on shorter time scales. So, she is projecting that also onto what we called active and break spells, or the monsoon intra-seasonal time scales, and comparing two periods, 1951 to 1980 and 1981 to 2011, and showing with statistical analysis that the intensity of the active spells is increasing, which is consistent with the increase in variability and increase in extreme events. So, again you can see that the focus is on the core monsoon zone and the coastal regions where there is heavy rainfall anyways. And she also shows that the extreme dry spells are becoming less intense, but the frequency of dry periods or break periods is increasing. Okay? So, we looked at the distribution of rainfall for a few years as an example here, and said that during a dry year typically you have longer break periods and fewer active periods. So, what she is saying is that this is just for particular years. She is saying if you look at the distribution of all the years over this period and plotted it exactly like this, then that also is changing in this way, where the break periods are becoming more frequent and the active periods are becoming more intense. So, again it re-emphasizes the message that even though we always think of monsoon as a season and seasonal rainfall, the distribution matters, and every change that happens in the monsoon, either it is because of El Niño or La Niña, or because of global warming, or even because of ice ages, it always seems to project onto, or it always appears as changes in active and break periods or intra-seasonal oscillations. That is kind of bad news in the sense, if crop calendar depends on active and break periods, then we must be able to understand better the active and break periods and how to predict them and so on. So, I will show some predictions at the end. Okay? So, these are kind of again multiple messages, but they are all consistent. Extreme events are increasing when you look at the rain rates, like greater than 100 millimeters per day or 150 millimeters per day, and that means when it is raining that much, it is an active period. So, active periods are getting more intense, and we know that when droughts happen there are longer break periods, which means if mean rainfall is decreasing, then frequency of break periods has to increase, right. So, it is all consistent, but it is just expressed in different ways. This is now looking at the longer term trend going from 1900 to 2012 or so, and it is showing also a map of the trend in rainfall. So, trend means you basically take the rainfall here and the rainfall here, and you subtract and divide by the number of years, and that gives you a straight line. So, this is the warming of the sea surface temperatures we mentioned before, and this is the decrease in the mean rainfall we just mentioned. But the rainfall obviously has a pattern. It shows that there is some kind of a horseshoe pattern in the rainfall. This is showing the correlations between Indian Ocean sea surface temperatures, Western Indian Ocean sea surface temperatures, and the India Meteorological Department precipitation data. And this is showing the same thing with a different sea surface temperature product, and arguing that both have very similar patterns, where over a large part of this core monsoon zone there is a negative correlation, which means a warm sea surface temperature is causing a decreasing rainfall. So, the correlation will be high because both are trends, as we said, but this map shows that there is a pattern to it, and so then you can begin to look at more rigorous attribution to say how is it that warming sea surface temperature is reducing rainfall over India in this pattern. Obviously, you can already begin to imagine that if southwesterly monsoons winds are involved, then warming over the ocean must somehow affect either the circulation or the amount of water vapor coming in with the winds, or both, correct? That's kind of how we go about. So, you have to always look for the causal links between the two quantities that you are correlating. I already mentioned this, but let me re-emphasize. So, this is the seasonal distribution of rainfall for last year, which is 2017. And in 2017, it was considered basically a normal year in the sense if we average rainfall over all of India, it was probably within about 4% of the long term mean. So, it was within 4% of the 900 millimeters or whatever the current mean rainfall is when you average over a few decades. But you can see that that does not mean that it has been normal all over India. So, it had rained a lot over these western parts, Gujarat, Rajasthan and some parts of interior Maharashtra, Karnataka and peninsular India. It in fact had some deficits over coastal regions and western Ghats, and it had significant deficits. So, the red colors here are deficits and the green colors are near normal and blue colors are excess rainfall above normal. So, large regions were actually below normal, but when you average it looks like all of India was near normal, which is okay because it turns out that the total amount of rain does correspond to grain production and it does matter for water availability for industrial use, domestic use, agriculture and so on. So, there is a value to look at the all India averages, but when you talk to farmers, obviously farmers sitting here want to know how much rain they are getting and they will be affected by having a deficit over the season. So, the main point is that even when all India monsoon rainfall looks normal or near normal, the distribution can be very uneven and some places can have severe droughts, some places can have excess rain and floods. So, this is what we mean by extremes. Even though the distribution may look normal overall averaged, the frequency of active periods, break periods, intensity of active periods and so on has to be looked at because that still produces floods in some regions. This year 2018 has been really devastating, especially for Kerala, where the losses are now into several $billion or lakhs of crores of rupees, and many people have died, which is never good news, and recovery will take a long time. But if you look at the rainfall, what we would actually expect by this time, June 1 to August 15th, we would expect a lot of rain in the coastal regions and some parts of Himalayan foothills. We would expect less rainfall, around 200 millimeter over drier parts like Rajasthan, and rest of India should be in the range of 500 to 700, 800 millimeters of rain. And if you look at the distribution, this is for 2018, this is what we would expect normally. So, heavier rain here and drier patches here, which this region gets more northeast rainfall, for example, and this is what happened during 2018. And if you take the difference of these two, you will see that there have been normal or excess rains in some places, but there have also been deficits in large parts of India. So, large part of core monsoon zone is more than 10% below normal. Gujarat is almost 20-30% and northeast is almost 40-50% below normal, whereas this little corner of Kerala has gotten more than 40-50%, and in fact some of the districts have had 10 times the normal rainfall within 1 or 2 days, like August 12, 13, 14, those days when the floods happened. The rainfalls have been very extreme. So, this is what we mean by the changing distributions, where the mean can reduce and still the extremes can increase. So, this is an excellent example. So we'll look at some particular relations that we already know of. El Nino we talked about, where during normal time you have warm sea surface temperatures here, cold sea surface temperatures here, high pressure, low pressure, convergence, rising air, sinking air. So this is the Walker cell that we talked about, and we said during an El Nino this water sloshes this way, the convection also moves with it. So you have droughts, forest fires and dust storms over here, and you have floods and mudslides and so on this region. And we also said that when this happens, when this warm water moves away from the coast of Australia and New Guinea, India tends to have droughts. So this is showing the rainfall anomalies over this period from 1870 to 2015 or so, or 2017. And you can see that we have looked at this once already, I think. There are many years where there are severe deficits, and there are many years where there are excess rainfalls. And the red circles and the blue circles here correspond to years that are El Niños and La Niñas. So when there is a La Niña, we expect excess rainfall. When there is El Nino, we expect deficit rainfall. It turns out that actually not all excess years are explained by La Nina, and not all dry years are explained by El Nino. So monsoon has its own mind as well. And as I said before in another lecture, we also don't know what the monsoon which occurs in June, July, August does to the El Nino, which actually is maximum strength in December, January, February, which is 6 months later. So there is some research going on which tries to see if the monsoon can somehow affect the growth of El Nino, but nonetheless, from climate prediction point, we should be aware that there is a high possibility that El Nino will reduce the rainfall, La Nina will increase the rainfall, but there are years when we don't know that. That matters because El Nino is typically more predictable. It can be predicted 6 to 9 months ahead of time, which means even 3 months before the monsoon season, sometimes El Nino predictions are issued. They may be wrong sometimes, like in 2012, 14 and maybe in 2018 already they had called for an El Nino, but it doesn't seem like an El Nino is coming. And monsoon has been so far mixed. We have to wait till September to see what the overall number will be, but we can see that there are large dry regions and there are some very wet regions. So we have to be careful about where the predictability of monsoon comes from, because it is useful to predict all India monsoon rainfall, and maybe it is easier in some ways, but we always must be able to predict the distribution of rainfall and hence the active and break spells as well. So I mentioned El Nino and said we don't know where the predictability comes from all the time, and that nicely segues into this study by a young scientist and student from IISER Hyderabad, which has shown with several papers now that the El Nino and La Nina like behavior in the Atlantic Ocean also affects the Indian monsoon. Okay, we didn't talk about this. There are El Nino like behaviors in the Indian and Atlantic Oceans as well, but because these oceans are much smaller than the Pacific Ocean, the El Ninos here do not last for 9 to 12 months as they do in the Pacific Ocean, which is very big. And that has something to do with the waves that travel in the ocean that are associated with El Nino and La Nina, and how long it takes for the waves to reach the other coast and come back. So if they are generated on this part, it has to go hit this coast and come back to change the process. That takes only 1 or 2 months in the Atlantic and Indian Oceans, whereas for the Pacific is much, much bigger. So it takes 9 months to do that. So it's 3 times longer. So nonetheless, this is called Atlantic Niño instead of El Nino, and it also has a warm El Nino and a cold La Nina like feature, and it turns out that it has significant impact. So this is showing the difference in Indian monsoon rainfall for a cold Atlantic Niño year and a warm Atlantic Niño year. And you can see that it has a huge signal here, which means the cold Atlantic Niño produces excess rainfall in this band and deficit rainfall in this band compared to a warm Atlantic Niño, which means warm Atlantic Niño also reduces Indian monsoon rainfall. And you can probably now begin to imagine how is it that the signal is coming from the Pacific side through the El Niño as well as the Atlantic Niño. What connects the two? I think you already know how that could happen, because you have learned about the ITCZ, which goes across the whole globe. So, if something is changing the ITCZ, ITCZ, is it possible that the ITCZ can communicate from the Atlantic side as well as from the Pacific side? Turns out to be approximately true. There are other details that we will not get into, but already I showed the ITCZ before when we started this lecture. So, you can just keep that in mind, that ITCZ may be some kind of a conveyor of these signals globally from both sides into the Indian monsoon. So, this is again looking at the trends in precipitation that we talked about, and this is now showing the trend in the frequency of extreme events, again defined as greater than 150 millimeters per day. This is a nice paper by a young scientist from Indian Institute of Tropical Meteorology called Roxy Matthew Cole, and he has shown in a recent study that came out last year 2017 that the number of extreme years used to be about 2 per year, but by now they have reached about 6 per year. So, there is a threefold increase, and he shows that the patterns have become more widespread. That means, the popcorns used to be smaller before, but now the popcorns are popping on a larger part of the core monsoon zone. So, the floods are not just happening over Bombay or Gujarat, it is happening over this large swath of India going from the central western part to the central eastern part. Okay? And there are some signals here as well. And you know that Kaziranga has had floods, Bombay has had floods for several years. This year 2018 Kerala got hit very hard. So, there are all these changes happening that are clearly detected in the rainfall data that we have. So, I will get slowly into the attribution, what are the causes for these changes in extreme rainfall. So, we said when global warming happens, evaporation increases, humidity increases in the atmosphere, and we said 1 degree warming gives us 7% increase in humidity, because there is a non-linear relation between temperature and humidity. As we said, warmer air holds more moisture, but that moisture increases non-linearly. But the rainfall, mean rainfall only increases by about 2 to 3%, because that condensation and rainfall has to lose the energy to space, which is a slow process which is constrained. I am being a little bit simplistic in explaining it, but the actual dynamics are very complicated. And we said that the extremes can increase by 10 to 30% depending on where you are. So, that means the first thing you want to do is look at the relation between warming and extremes. So, Vitthal Bhatt, who was a student at IIT Bombay and now a faculty at some Manipal Institute, has done this nice study where he showed that if he looked at the relation of the air temperature at 2 meters and extreme rainfalls over India, large part, about 73% of the boxes over India do not show any relation between local warming and local extreme rainfall. Okay, only 26% of the boxes over India show a relation between local warming and local extremes, which means what? That means unlike on the ocean where there is a lot of moisture available, local warming can create local evaporation, local supply of moisture and local extremes. over land, when you heat and create conditions or instabilities for demanding excess rainfall, the moisture has to come from somewhere else. That is why you do not find necessarily a very high number of boxes where the local warming shows a relation to local extreme rainfall. Okay? So, where does the moisture come from? This is just showing again the frequency of extreme events and frequency of widespread extreme events. Widespread basically means they are occurring over a large box which was defined as a 10,000 square kilometer box. So, whenever the extreme rainfalls are spread over such a large area, Roxy calls it widespread extreme events, and he shows that both of them have gone up, and the number to remember is widespread extreme events used to be about 2 per year 50 years ago, but now they are about 6 per year. That is not good news, because in a year India loses something like $3 billion due to these natural disasters. So, we must keep an eye to see if this is really continuing to increase and how to better predict them and how to mitigate their impact through reducing deforestation and various other measures of drainage in the cities, protecting infrastructure, transportation, and so on and so forth. So, lots of issues on how to deal with disasters, mitigate their impact, and faster recovery from disasters. Okay. Let us now try to look at some of the sources for moisture. Before, I mentioned briefly that there are West Indian sources, Upper Indian and Central Indian sources, and so on and so forth for moisture to monsoon rainfall. So, for the extreme events also you have these sources. This is kind of a figure that is a bit hard to explain, but essentially what you do is, if you want to look at the rainfall over this region, then you track the water back and see where it evaporated and when it reached here. So, you take the time that extreme events happened here and show that the moisture is basically coming from the Arabian Sea, which is about 36%. When moisture comes from the Bay of Bengal, it is contributing about 26%. Moisture from Central Indian Ocean, which we defined is somewhere here, is about 9%, and the recycled precipitation from Central India itself contributes about 29%. So, the figure is complicated, but essentially when there is supply here, it is going to come from here. So, it looks like it is losing moisture here, which is accurate. This is showing moisture is being lost here, which is not being seen, moisture being lost from Bay of Bengal, and so on. Okay. So, when you have widespread extremes over this region, majority of the moisture is coming from the Bay of Bengal, and a lot of it is being recycled locally. So, if you have a huge flood, that can begin to evaporate and fuel extreme rainfalls over the same region. Just like then it becomes like an ocean, right? So, this contribution could be due to irrigation from previous rainfall and so on, but nonetheless on the ocean this is what happens. If you heat it, there is enough moisture to evaporate and supply itself. So, you have local relation between warming and extreme rainfall. So, note that Central Indian and Bay of Bengal contribution together are less than the Arabian Sea contribution. What did we say about the Arabian Sea? We said that the Arabian Sea is warming fairly rapidly, right? There is another thing, it turns out that even this part of Asia, Pakistan into Afghanistan and the Himalayan foothills are also warming. Pakistan had more than 50 degrees centigrade during 2016 and 17. I think this year they haven't had such a heat wave, but they consistently have very strong heat waves during the summer months. So, what happens if you have warm sea surface temperatures here and warm air temperatures and land temperatures here, depending on who is warmer. So, let us say this is warmer, then you know that this pressure is going to be lower, this pressure is going to be relatively higher. So, you are going to have winds wanting to go this way from high pressure to low pressure. Now, you use your Coriolis. What would you want? This wind then would be turned to the right. So, Arabian Sea warming is producing more moisture, right? That is the first thing that happens. And the land warming is producing this pressure gradient, which is producing winds which are adding to the winds that are already coming from the southwest. So, the land ocean heating contrast on the large scale is giving us the southwest winds, and then locally you are also creating additional winds and additional moisture. So, those are pumping huge amounts of moisture into these widespread floods. This is the attribution aspect of the relation between warming and extreme events. So, it is always very detailed process, models are used, data is used, statistical analysis, dynamical analysis, thermodynamical analysis are done. Dynamical means winds, moisture transport, thermodynamical means evaporation, condensation, clouds, rain and so on. So, is this really working this way? So, if you look at the long term trend, we said this is the region of widespread extremes going from 2 per year to 6 per year. If you look at a particular day like 2nd August 2016, where there were massive floods over Bombay, but those floods were also quite widespread over the same region. So, that means that the long term trend is already being acted out in each year since about 2012 or so. We have had many floods in 2012, 14, 16, 17 and now 18. So, this is not something that we can take lightly. So, this is how the monsoon is responding to the warming that is happening not only over the ocean, but also some parts of land. Okay? So, let us try to kind of then put together the whole monsoon response in a broader context. We said monsoon has an onset and a withdrawal, right. So, this study by Sahana, who just finished PhD from IIT Bombay, showed that this is showing the onset on mean, long term mean, which is let us say something like June 1st, and she is looking at the deviation from the long term mean for periods before 1976 and for periods after about 1976, which is turns out to be a year where there was a rapid acceleration of warming and some kind of a climate shift that happened, that is seen in everything from thermoclines, sea surface temperatures, zooplankton in the ocean, fish, salmon, sardine, anchovies and so on and so forth. So, there is many evidences across all the world that some kind of a shift happened, and she shows that the monsoon onset typically used to happen earlier than the mean before 1976. After 1976, the monsoon has typically been arriving a few days later than it used to. Okay? So, you can see that the onset date varies quite a bit, but still there is a shift to a slightly later arrival. And this is confirmed with looking at various distributions and so on. And the distribution has clearly changed in terms of onset days for the period 1948 to 1976 compared to the period 77 to 2011. Okay? So, remember we said the monsoon season has an onset and withdrawal. If onset shifts, then we have to also look at what the withdrawal is doing and then see what it means for the length of the rainy season and what it means for number of rainy days and extremes. So, extremes we already said widespread ones are increasing. So, let us stop with this figure, which is showing some nice work by Sabir Ali from Indian Institute of Tropical Meteorology, which showed that during the same period the withdrawal has been occurring typically few days earlier. The withdrawal in general happens somewhere in the third week of September, and he's shown that with the climate shift, the withdrawal has been happening earlier and the length of the rainy season has gotten shorter. Okay? So, it is not just that extremes have increased, onset is delayed, withdrawal is earlier, and the whole rainy season is being squeezed by a few days. So, we have to put all of these together. The mean is decreasing, length of the rainy season is decreasing, and extremes have increased, which means if you decreased the mean and reduce the rainfall length of rainy season, you can distribute the smaller amount of rain over smaller number of days and have even distribution of rain, which would be nice for the crop calendar because they can adjust the growing season and sowing days and harvesting days and so on. And in fact, in older days people used to store, let us say, varieties of millets which can be harvested in 2 months, 3 months and 4 months and so on. So, based on when the rain started, they would use the appropriate variety of the seed. Okay? But now we are saying that the rainfall season has been squeezed and the decrease in rainfall is more than compensated by this huge increase in extremes, and the extremes have become more, not only more frequent, but more widespread. So, there is a threefold increase in these widespread extreme events. We will come back and try to put some more details of what else has changed and what it is that we are doing about it. What are the models saying? How good are the predictions? And what can be done in order to use the predictions to mitigate the impacts, which means get better prepared for the impacts and also to better faster recovery after the disaster happens, like Kerala. Now, we will be watching very carefully because it was such a large scale devastation. How are the recovery operations working and how quickly everything will come back to normal? Obviously, it will not be few days or few months, it will probably be few years, but still it is very valuable to learn lessons, because from the 2005 flood in Bombay, we learned a lot and showed that by 2017, when the big flood happened, many changes were made in the decision making process of warning people, closing schools or working from home instead of going to office and so on. Number of deaths were reduced. Of course, there are other details like changing building codes, not allowing building on dangerous slopes or removing vegetation from slopes and so on and so forth. But we will see that there is some good news among all this devastating news about increasing widespread extremes and so on, that India is making better predictions. So, we will discuss that when we come back. See you next time.